In this class, we will talk about aerospace structures itself. So aerospace structures in general, when we design them, we have a primary load path and a secondary load path. A primary load path is one that is going to carry most of the weight of the, it's going to be responsible to carry most of the load. A secondary load path is one that may not necessarily carry the major load. As for an example, if I design, if I put two spars like this, right? And these are spars. So you could design them maybe something like this. These are spars. This is a C-channel spar. And now I design my plane. On top of the spars, I place I put some skin on top of it, right? If I can get this right, something, skin. And this is kind of your airfoil. And it goes like this. So, and then also you have here, you can have ribs. Ribs are attached here. So you got ribs here and you got ribs there, right? So these are ribs. Typically they are full of holes. And so this is your structure. This structure right here, this structure, this structure, this structure is the main loading structure. Now you have a secondary loading structure that would be your wing, your skin. You could have maybe a stringer that's attached to the small stringer that's attached to the wing itself, the skin itself. Many times when you look, if I look from the side, you will see that you got your spar, and then you have what you call a T-string, a stringer that would go there, and that is just a load path that I create to help for stability purposes of the panel itself. So it's important when I'm designing something to know what I can, if something is going to fail, I will most likely want it to fail in a secondary load path than the primary load path. You can think that if I lose one of the spars, if I lose this spar itself, now this spar doesn't exist, the possibility that this whole thing is going to collapse are huge, because this is what's really holding my entire aircraft in its place, my airfoil, I'm sorry. So this part cannot fail under no circumstances. Neither can this. This is what we call a wing box. It's holding the whole wing box in its place. And the secondary load path and structure is, okay, if it fails, at least I can land. My airplane will be able to land. So in a general, a typical wing construction, and this is for semi-monocoque. We will talk about this later. Monocoque. Semi-monocoque is one that has skin. These are ribs. This represents stringers, and these are the flaps, and this is the wing root. So this is where your airplane is really attached. So when you look at this whole thing here, this is the leading edge. This is more or less what it looks like. If I go a little bit more detail, you will see that this is what we call vertical stiffeners. This is what we call the front and rear spars. These are ribs right here. And the ribs have a purpose why they got hole. The reason behind they have holes is, first of all, make them lightweight. Secondly, that's where your systems engineering is actually, all the electricity, everything else that needs to be gone through from one spot to another, that's where they will be located at. But we design these holes. We design how much the dimension of these holes can possibly be. Okay, so this is a case where you have a wing with only spar only. This is spar only. This is a case where you got spar, you have a spar, and you have stringers. Okay, so this is mainly a monocoque construction, because it's saying that your entire structure, think about the wing, and I will make the wing as thick as possible, and I want the whole structure to hold all the loads. As you can guess, this will be a heavier construction. But now when I come to this part of the design, now I can say, hey, this is only skin, and this is what's really carrying most of my weight. So these are mainly the load-bearing main structures, and everything else is secondary. This is if I just remove the skin, it will look something like this. Yeah, these are not cylindrical, okay? They are sometimes T-shaped, sometimes L-shaped, sometimes inverted T-shape, but this is where your skin is at top here, so they're all attached there. So this is something like this, so they can attach. They're attached with rivets or fasteners. Your fuselage is a giant cylinder that basically has longitudinal stringers and also transfer frames. These are frames. And this is the skin cover. And what we want to study aerospace structures. And I like to learn from history. Like, for instance, this particular airplane really just ripped apart right in the middle, right? And as soon as it was landing, and the landing process is just ripped apart. And if this is going to fail like this, typically it fails because it fails where the rivets are. And when I talk about rivets, it's basically you got two panels, okay? And these two panels somehow are joined together, and they are joined through rivets, okay? So underneath this, you have something that join these panels together, maybe a I-beam or a C-beam typically. And then so if something is going to break, it's more likelihood it's going to break through the joints. And this is a very good example in where you have not only failed through the joint, but failed through the whole wing itself. And this is example, as you can see on this section right here. Let me change the color. These see wrinkles. There are lots of wrinkles there. That's what we call the skin buckle in that section. This is another example in which you may see an airplane like this, and you may get freaked out, like what happened, got burst strikes. Actually, it was not burst strike. It was structural failure, because the ribs on the inside that hold everything in place, they collapsed. So the pressure was higher and actually made it fail. So when your airplane lands and they look at stuff like this, first of all, you should be thankful that nothing happened to the plane. Secondly, you have to ground the plane and repair it. We cannot get around that. That is very important. A very typical case, a couple people died in this accident. It was 1988, Aloha Airlines. And what really happened was, along the rivets start peeling off. So one peeled off, the other peeled off, and eventually the whole thing peeled off, and the whole upper section just flipped apart, right? And so these are important considerations that we take in we are designing planes. We definitely don't want that to happen, and history teaches us many of these lessons. This is a more recent failure that we saw. This is in 2011. This is Southwest Airlines. It's a Boeing a plane, and you can see that during the real flight time, this part really ripped apart, and there are some other minor damages that actually occurred in the plane itself. You can probably observe, you can see them here, and this is the same, this is a zoomed out view of what this really looks like. And you don't want this in a plane, a real flight. You definitely don't want it. But if it does happen, we have to design it such that we design a plane. So this is very different from every other structure that you design. Here we design a plane, and we say if it's going to fail, this is how it's going to fail. I want to make sure that it fails such that it fails safe. I want people to be able to be safe. I care for the security of the people, safety of the people. So we have to intentionally design what your primary structure is, your secondary load path is, and say if there's a failure, I want it to fail here. I don't want it to fail the whole thing, right? So if you got the whole wing box, and the wing box fails in your main spar, rear or leading spar, and you have those spars that fail, you lost your aircraft. But if it fails in your mid-spar, then okay, I can still drive and maneuver to land my plane. So we have lots of inspections that go on between flights, or at least they should. And typical airplane does have a couple cracks, and those cracks are measured to make sure they're below some critical fracture length. And later on in this class, we will teach you how to do that. Basically, possible cases of failure, these are when they're minor effects. The major effects is what we really, we get freaked out. Any of these the hazardous effects, and then you get catastrophic effects, right? These are when you lost your aircraft and their casualty. Take a couple design. The first of design is infinite life. When you design a structure, as you can imagine, I will design a plane and it will say this plane is going to last me forever. You don't want that at all. You don't want a plane to last you forever. Why? Because it's going to be costly, heavy, the materials you're going to use. So you design a plane. That's one way to design it. In some few applications, maybe there's a case where you want to design an infinite plane, infinite life plane, but you don't. You design a plane mainly for certain service criteria. It may be designed for 20 years of life and we are done with the plane. 30 years of life and we are done with the plane. Now, there's a different philosophy depending on who is buying the plane. Like, for instance, the commercial aircraft, they will buy a plane that typically has a lifespan of 25 years, but they will keep on doing repairs. And those repairs that can take the plane up to 30, 35, maybe years. But the repairs are not cheap. They're very expensive as well. So it's a trade-off in terms of when you stop repairing and say it's time to replace the fleet. Okay. In the Navy, Navy cares for designing me a plane for 20 years. After that, dump it. I don't care for it. Air Force, on the other hand, they care for damage tolerance, in which they care for if I can get 5 more years from the plane, 2 more years I will. So the philosophy is different for both of them. Then you design a plane for their geared towards their needs. Okay. So with that said, the second criteria is the safe life criteria. We are basically saying that, well, there is a damage in your problem, in your aircraft, and that damage is going to be given, that damage is located right anytime over here. So if I have a damage, it doesn't reach my critical damage criteria, so I can still fly my aircraft. And I want to make sure I'm not sure if you can appreciate this, but let me see if I can zoom this so you can really appreciate this. So when it hits this mark right here, it's not failed. He has not failed at all. Okay. So that's what we want to do. We want to make sure that there's a cutoff that you want to take into consideration, and you want to stay below the critical. And after that, you just dump the airplane. You don't need the airplane anymore. Damage tolerance, on the other hand, is very different, because damage tolerance is based on a constant inspection. And if there's a damage and we can repair that damage, we try to repair it and bring it down here. And then we constantly are repairing and repairing and repairing. And this will be the location in which I can no longer repair my airplane. But I will stop, have a cutoff somewhere over here after many different damage criteria. But the trade-off with with damage tolerance now is you need to create a secondary load path. As for an example, I wanted to consider the pressure cabin of an airplane. It's comfortable, but what happens if the airplane actually there's a pressure problem? Well, then there is a mechanism to actually address that issue within the plane. Let's suppose they got 2 bays. This bay that has a crack in it. Well, if this does have a crack, I want to create this load path. So if you would, I lost this panel because of this crack. So this can no longer hold the load, but can these 2 crack arresters hold enough load to make my plane land? And so I can repair this later. So these are the different things that you have to keep in mind when we're designing planes. Another very interesting case is what happens when we have two engines. Typically, a typical airplane has two engines. And the reason behind it has two engines is if one engine fails, you can fly with the second one. The extreme case is the case of the Hudson River. I'm not sure if you have read it or you heard about that in the history books. But that plane was very phenomenal because both engines failed, and the pilot has a matter of a seconds to make a decision. Do I try to turn and land? Do I land in water? What do I do? He sees the Hudson River, and then he says, I'm going to land in the Hudson River. Just wait for me there. And he makes a very awesome landing. That's actually everything goes in such a case. You have to give credit to the pilot. And thank God that you didn't have any other further structural failure in which your plane was actually able to land. So we aerospace engineers, aerospace structural engineers, are responsible to design planes such that they will be safe in every possible circumstance. Okay. So we have what we call multiple. We got the backup systems, and we have multiple load paths. We don't want to rely only on one load path. That's why we have more than one spar, more than one rib. If one fails, the whole plane can still fly. And that's why we have crack arresters, right? Because we want to make sure the weakest link will be the bay, and I will let it fail. So if it's going to fail, I make the path and I design this so it will fail here and not fail over here. Okay? So these are some criteria that we keep in mind when we are designing aerospace structures. And throughout the course, that's what we will try to, how do we design strong while keeping light aerospace structures to make robust airplanes. That's going to be the focus of this course.